Okay, so at the end, what we have to prove for these absolutely continuous functions that if f is absolutely continuous, then is equivalent to f of x is equal to the integral from, well, let's say from a to x of some function g. G is in L1 plus, let's say, f of a, and g and f prime is equal to g almost. So the fundamental theorem of calculus. Absolutely continuous functions are integrals of L1 function, and if it is absolutely continuous, then its derivative is an L1 function, and it is exactly the integral of the derivative. So far what we know is the definition of absolute. So on one hand, we have this is a nice object. In some sense, we can compute it. On the other hand, this needs a definition. The definition is that f is absolutely continuous if for all epsilon there exists delta. Let's say if the measure of an open set is less than delta, then the sum, but these are intervals, so let's say O is the union of the joint intervals AI and BI. So the sum of the variations then epsilon. And for us, always we assume that F is defined in a compact set, bounded, and this continues by the definition. So we are left to prove essentially that this part over here. So what we know is that from this fact we have that so some properties. So if f is absolutely continuous, then f is BD. You remember why?
Yes.
Because we can compute the total variation of this object. So how it works? Well, essentially, if you split the interval, you remember, you split the interval into pieces of length delta, and then you are sure that the total variation inside each piece is less than epsilon. So the total variation of B of F in A, B is less than, okay, less or equal than B minus A divided by delta, which is the number, which one is delta, times epsilon, which is the variation admitted in each interval. And so we deduce that F, well, and we can say also it is continuous. But this is trivial, no? Because the definition implies the continuity. Just take one interval. F is equal to, let's say, the sum of G minus H, G, H are monotone increasing. Bounded. Simply because for BD function it holds, and then it holds also for absolutely continuous function. Okay, so the third fact is that then we need just to prove this result for monotone functions. The integral is linear. F is the sum, so it's a linear operation. So we need just to prove that for monotone absolutely continuous function, the theorem holds. This property holds. Only F monotone increasing and absolutely continuous. So what
And then consider only.
Yes, this is a yes. No, that the fact that now you just type, it means that you don't write almost anymore, and then the calligraphy gets worse and worse, and then it becomes like Chinese calligraphy when you don't understand it.
But you should understand it.
It's easier for us.
But actually, at the end, since I train my mind to interpret my bad writings, I can read. It's just it's like a local dialect. I'm the only component of the tribe. But it's true. So, for example, now the engineers, they just type and they don't know how to write. And actually, it's even worse for a drawing, no? Because you don't need to do any technical drawing anymore. You have these programs, they do it. So you don't know how to make a technical drawing. But of course, it is not, probably is not needed anymore, it's a requirement. Okay, so we simplify the set. So let's see what we know, what we can do. So I'm not following the book. I prefer to construct everything from scratch because the main result is the following. So we need to prove essentially that this integral hold and this equality hold. Clearly we have the opposite. At least if this is differentiable, so if we try to make this, then it is absolutely continuous. We proved last time. So let's prove the opposite. So if f is absolutely continuous, then f is the integral of the derivative for every interval. And then the second part is that the integral of the g is exactly the derivative. You cannot have two g's. So we have two problems, 2 points to prove, no? First, that f is exactly the integral of the derivative. And if f is the integral of g, then g is the derivative. Okay? So which one you prefer first? They are independent in some sense, because you can prove that g is equal to the derivative, and then the integral of the derivative is f, or
Maybe to prove that the derivative is
the derivative exists.
No, it's easy.
To prove that that g is the derivative. Yeah. Ah, okay, sorry. Here there is a last point I forgot to say. G is the BV, and then we have that f prime exists almost everywhere. Because f prime is what? But if I have solution continuous, I know it is BV. I know that it's the difference of monotone increasing function. Lebesgue theorem assures me that monotone function, they have a derivative almost everywhere. And another thing I can say is that essentially for monotone function, the integral from a to b f prime is less or equal than f of b minus f of a. So one part of the inequality is done. Okay, so let's prove that they are equal. No, you prefer first this step. So we rule out the fact that you can have several derivatives. Okay, so this is like an exercise. Assume that f of x is equal to, well, we can forget about f of a. This is the constant. A to x g of y dy, and is equal to a to x of h y dy. Then g is equal to h. Almost everywhere. This is the statement. Because if I prove that here the equality holds, clearly b can be x, because if it is absolutely continuous in a, b is absolutely continuous in any interval inside. And also if I have the equality, then it means that for every x, here I can put f prime, or here I can put f prime, because I have the theorem. And then if I have another g, I reach this conclusion. The integral should be equal for every x. Reduce, then, it's written, then easy. Okay. So now, is a nice exercise. How to prove it? Remember here that for all x, not for one single x, no? For one single x is false. The one is integral 0 is not 0, you just take minus the function and then. Okay, how to prove it?
Can we assume that those are monotone and increasing, or in general?
But then you still don't know, no? Because maybe when one is positive, the other is negative, and you cannot compare, you still have two pieces, no? I'm not saying that each piece, the positive is equal to the positive, the negative is equal to the negative. At the end, yes, if they are equal, clearly, when I do the positive, the negative is the same. But here I don't see, no? Because the problem is that for a fixed x, you have a function like this, whose integral is 0 and the opposite 1. So who tells you that the two parts are equal?
But for every x it holds.
For every x, yeah, the problem is for every x, but how to use it? Okay, so I start and then I ask you. So set, let's say m of ax integral from a to x of g, and then n to h. Oh, well, let's say they come from h, so I recall that they come from g and h. Okay. Then g is equal to h for all a intervals of the form ax. You see the line now? It's very close to the line for measures, no? Indeed, they are measured with the sign in some sense. So what I do now? So they are equal for intervals this form. Then they are equal for take an interval of the form CD. Are they equal for open intervals where every open interval? Well, clearly if I subtract, okay, yes. Why? So I pass from these sets, I pass to these sets minus another set, let's say C, and then I pass to X decreases to or increases to D. This becomes CD. You remember for measure, so if you know that they are equal for example, if you have a measure which is equal to the Lebesgue measure for this interval, and you know it is a measure, so it has the property that you can pass to the limit of sequences, and the complement is the difference, then till you obtain open sets. Is that okay for you? You understand the passage here, or you want me to express to make it more explicit? Well, you just use G of this set. This set is Cx is equal to G of Ax minus G of AC. And now, if Xn converges, you know that G to D, G of CD is equal to the limit for n of the integral from xn to d, sorry, c to xn. Well, I wrote the integral, but actually it's the limit of g c xn closed. Because the integral has the property that if you have the sequence which converges, of the sets which are enlarging or downsizing, the values converges, like for a measure. And this is just the property of the measure. If two sets are disjoint, the measure is the sum of the two integrals. So the integral is the sum of the two integrals. Okay, so we reach that they are equal here for open set. Then, you see now the next step?
Take the limit.
Hmm? Then O open G of O is equal to H of O. And this is the sum, the integral from AI to BI of G, and this is the sum of the integral AI to BI of H. Is that true? Yeah. But I can also deduce is exactly the sum. Okay. Next step. Now I think you understand what I'm going to do. Finally, E is a measurable set. G of E is the integral over E of F, of G, sorry, of G, is equal to H of E, integral over E of H. Is that true? Yes, because I take a sequence of open sets converging to the G delta set whose measure is the same. So that this G delta set minus E has measure 0. So they coincide on the G delta set, and the difference is the integral over a set of measure 0, so the integral is 0. Okay, so I discovered that if this holds for this kind of set, I have that this equality holds for any measurable set. This is equivalent to the integral of E G is equal minus F is equal to 0 for all E measure. Okay. So it's I'm just repeating the construction of the measure in some sense. I know how to give value to a. If I know how to give value to intervals, I build a measure. And since they coincide with integrals, the procedure to building a measure is a direct procedure. So I'm just doing by limits. And so they coincide, because they coincide on the sequences. Okay, so how to conclude now? Now it's done. Take the set where where they are different. But actually I need still to say that the integral is non-zero. So I take the set where F y such that Fg y minus Fy is greater than 2 minus n.
Is it F or H?
H. Okay. Then the integral of this Wn of G minus H is larger, larger or doesn't matter, 2 minus n, the measure of Wn. The integral is monotone. But this guy is 0. guy is 0.
So it must,
So?
so it must have measure 0, or G minus F must be 0.
So this measure is 0. And then the set W, G is greater than F, then H is the union of Rn of Wn, and so the measure of W is equal to 0. Again, I'm using the... So I deduce that G is less or equal than H, and this is H. And then you just repeat for the other case, and you obtain that F is less or equal. So up to a set of measures 0, they consent. So I have now a question for you. Just philosophical characteristics. Let's say F is greater or equal than 0, then is assumption or a consequence. So I say that this is, for example, it is a measurable function. And is greater or equal than 0, and is exactly equal to plus infinity. So I would say something 0 times plus infinity, which is in the side. It's plus infinity on a set of measures. But the fact that I assume that this is equal to 0 is an assumption that I say that I'm assuming in the algebra that 0 times plus infinity is 0, or is a consequence of the theory, the definition. Okay, so now this I leave for. Okay, so now we are fine. This is done. If f is given by this, f prime is equal to g. So let's show that f is absolutely continuous, then the derivative exists, and if we have the equality. This is the last point. Because if we have the equality, then f of x is equal to the integral of f prime. But if f of x is the integral of g, then it has a derivative. It is absolutely continuous, so it is equal to also the integral of f prime, so g is equal to f prime. So the theory is concluded, no? So let me do the reasoning again. So if you prove that integral from a of x of f prime is equal to f of x minus f of a, then we have that if f is AC, the theorem holds. Because it's written here. If f is equal to the integral of g, now we know that being g in L1, f is absolutely continuous. Because we take a set whose measure is less than delta, this is the integral on a set of measure less than delta. We know that one single function is uniformly integrable. Proved last time. And then we know the first implication. And now from this implication we deduce, so the theorem is complete. You see, no, the reason. Some remarks. For example, why f prime is in L1? I'm not saying it, but we saw last time and we know for why. Okay, how to, so we have that f is equal to g minus h, g monotone, h monotone increasing. So increasing. And explicitly g is equal to f plus the total variation of f, so for f of x, if you remember, in ax, you remember, no? Because essentially, the idea is that how much I varies f later is certainly controlled by, so the difference from x plus y minus f of x is controlled by the total variation in x plus y. Because at least is the difference between the two endpoints. Then you can put points in between, so if it is non-monotone, you increase the total variation. So here I can have, they are bounded. Because the total variation is bounded and f is bounded. And now, so what is now? And then we know that the integral of g prime is less or equal than g of b minus g of a. The integral of h prime is less or equal than h of b minus h of a. So less than plus infinity. And so this gives that f prime is the sum of the difference of the two, and the modulus of f is the sum, is heavily bounded. Actually, in the proof, I can say just it's less or equal. Yes, it is L1. So this fact that G is in L1 I have two other points here, no? You see the two pieces, so I want to make a brainstorm picture here, like how to connect the pieces. So we are left really with only one implication. If F is absolutely continuous, the equality holds for every interval. So I just need one interval, no? So that is the implication. You fix X and then the equality holds. Do you agree?
Could you repeat?
Which one?
No. The last thing you said.
Let me do it again the picture. So the important theorem, the fundamental theorem in this weak setting is this formula. Absolutely continuous function is equivalent to the integral of the derivative. And the derivative is L1. Vice versa, if it is an integral of a function, L1, then it is absolutely continuous, and that function is the derivative. So like for a C1 function. So the integral of C0 is C1, the derivative of C0, of C1 is C0, whose integral is that function. Everything is like the classical setting, just you have to replace. Now we know how to integrate objects which are not just C0, or a little bit more than C0. We know how to integrate objects which can be, well, different. I would say different because it always depends on when you say something is closed or not. So you have your own topology in mind. But let's say something objects which are, they seem very much more complicated, and then you ask the question whether this fundamental theorem holds. And you discover that there is a class which is not, is a class which is a subset of the continuous function, is larger than the C1 function, but is a subset of the continuous subset of BV. It contains the Lipschitz, so you can do a lot of inclusion, but essentially, so you start like this. So you have several pieces, no? So you can assume that it's absolutely continuous. So you can prove the implication then that f of b minus f of a is equal to the integral, you deduce, first you deduce that f prime exists almost everywhere, and f prime is in L1. So I can integrate. And moreover, you have that the integral of f prime is less or equal than f of b minus f of a. Sorry, the integral of the modulus is less or equal than the total variation should be. And f is equal to g minus h mod. So these 2 points are the same, no? It's that preliminaries. And then just study for monotone. If the equivalence holds for monotone, then it's fine. So if integral g of, let's say, g is equal to g of b minus g of a for g monotone. And then deduce integral of g prime, sorry. Then deduce that if g is the integral from a to x of another h plus g of a, then h is equal to g prime.
Almost every or?
Yeah, almost everything. Now, you deduce that if G, so if this holds, you deduce also that F is absolutely, I should come back, sorry. This should be. So then you have the following step, let's say intermediate step. If f is equal to the integral of f prime plus f of a, then f is AC. Then I close the circle. So if this is absolutely continuous, I have a derivative which is in L1, I have a control on the L1 norm, then it's monotone, so if this holds for monotone, I deduce that this holds for my function. And moreover, I know that if this holds for monotone, then this h, if there exists an h for which this formula holds, implies that h is equal to g prime. There's only one function h which makes the job, which does the job, and it is exactly g prime. But then if I know, so essentially if I see, I can write f as an integral of f prime. There is only that formula. But if this holds, I know it is absolutely continuous. So I close the circle. So the only step missing now is if it is AC and monotone, I have the equality. This is the last part, because we prove now this implication. So this implication. This was proved last time. Well, this is exactly just the definition, just written in another way. The definition of uniform integrability. And this fact was done for BV function. up to monotone. So the only missing point is if this hold, then I close the circle. So this is the only missing point. G monotone, bounded, the integral of G prime is the difference. So let's take it and then we build the proof pieces by piece. G monotone, absolutely continuous in an interval, and well, let's fix AB because if it holds for any, well, if just restrict it is still there. Then the integral of prime is equal to f of B minus f of A, and then I'm done. Okay, we need to put the pieces that we know and then to fill the gaps. So which pieces do we know? First piece, the derivative is almost everywhere. So the limit from h which tends to 0 which is the very definition. This is the very definition of the derivative. Why I can say, okay, so. Another piece that we know, so let's say is preliminaries. These are like the preliminaries. Oh, okay, so question. What are we going to use here?
Variation. Variation or no. I'm thinking about this. For example, if there's monotone and absolute continuous, so integral f prime is equal to variation.
To the variation, which is for monotone is less or equal. Yeah, is equal to the variation. Yeah, but yeah, but look at this one. I want to point. So we have that essentially take now a sequence instead of a continuous limit, a sequence, which is the same. You know, the limit exists, also subsequence converges. So it's like it's just to pass to the limit. Something. Indeed, this the formula, the less or equal. If you remember, we use Fatu. So we pass to the limit, but since we don't know, okay, recall. For f, the integral of f prime less or equal than f of b minus f of a, we use Fatu, which is the integral, the limit of the integral of what? So that object, which is so here is the difference. I need some more space. So here I would put that object. So this is the limit, the integral of Fatu. And then what I do here, okay, this part is fine. Because you see, I'm integrating, one is integrating, you remember the picture, no? I move by h, this part with the minus, and the part above with the plus. These are the two integrals of integration, no? Because one is from a plus hn to b plus hn. we did a trick in order to avoid to exiting from the interval of definition. Remember, we reduce a little bit the interval and we pass to the limit again. But if you imagine that this can be extended outside, by, for example, by a constant, then it is whole, no? And then, so you see, it essentially remains the integral over here minus the integral over there. So this is the limit, and then this is really a limit. 1 over h from b plus h, and f minus 1 over h n, the integral from a plus h n of f. You agree? And then this f is continuous, so the limit converges. So this is, the limit is exactly f of b minus f of a. Okay, so I need to improve this part. Because Fatu requires only pointwise convergence. If I want to have the equality holds, I need to use one of my theorems.
So, more monotone.
The monotone you don't know, however, that the convergence is monotone.
We just need so absolutely continuous.
The uniform bound, the Lebesgue theorem. Or something even more, we have a theorem that was a little bit more relaxed. More or less it's the same, but slightly more relaxed. It was Vitali. So if this difference, so let's say this is a function, let's call it delta A, well, this is exactly the function, is uniformly integrable. Well, of course, you can try and then you discover which theorem you have to apply. Let's make the lesson short. I know already which theorem you have to apply. Otherwise, in the real environment, it means your job, you have to try the theorems that you know. And maybe to see if they can be extended. You understand, no? But here I know already the theorem. So then, by Vitali convergence theorem, I have that the integral of the limit of diff hn for a sequence which converges to 0, let's say hn tending to 0, is equal to the limit for hn tending to 0 of that difference. And we know that this limit is f of b minus f of a. So with respect to the previous proof, I just, if I can prove that for absolutely continuous function, this sequence of functions, or this family of functions, is uniformly integrable, I don't use Fatu anymore, which just give me the inequality. I can use a theorem which gives me the equality. So that the idea is the same, it's just that I need to add something here, and then what I add, after checking, trying, after trials and error, I discover is uniform integrability. Understand? So that's the point. And now, once you discover this, it's just technique. So the idea of the proof is this. And then the technique is to prove that these hold. Okay? You're fine? So let's prove this part. Okay, so first step is what does uniform integrability mean? So what I have to prove? Well, of course, what you have to show, you take the theorems that is a priori, no? You take a theorem and says, okay, let's see if this theorem works. The assumption is monotone convergence. And then you look, well, why they should converge monotonically, no? Because, okay, I see that, for example, if you take a function like this one, the derivative switches from 0 to 1. So it's not monotone convergence. Then uniform convergence. Well, you think why I should have that the ratio should be should be controlled by a function, no? Because still I can have something which increases too much. But actually it's not that bad. I think if you work a little bit, probably you can get that you have a, but no, probably not. So I can still have something which you see the ratio increases and decreases. But certainly I know that the part where increases cannot be too large. Let me arrive to the proof. No, you cannot have that in a large, for some h, the set where the derivative is large is too big. Because then, you remember, we have Vitali covering theorem tells me that the image, so the difference, the total variation of f on this set is very large. You remember, we have this estimate. So we measure the set where f is larger than h, is less or equal than 1 over h, the integral of f. Okay, let me write. So recall the measure where f prime, or one of the interval, one of the approximate derivative, you remember, the sum of the limit, we can just take now f prime is larger than, let's say, k is less or equal than 1 over k f of b minus f of a. You remember, no? So this tells me that, yes, maybe they are really uniform integral. You see, no? This is done for the derivative f prime, but the bound is not depending on f prime, it depends on f of b minus f of a. So maybe it's the case that also for the approximation holds. So suppose that now we can put the measure where the difference is larger than k is 1 over k, then it is exactly uniform integrability. If we can prove then so what we are doing now is really we are decomposing the proof, no? Instead of giving just the proof. This is, we are trying to build the proof from scratch, from what we know. Okay. Well, but let's try first instead of, this is a reasoning which tells us that, oh, maybe is the case. And now let's try to apply the definition there. So take an open set O such that the measure of O is less than delta, and delta is very small. Now we have to compute the sum. So E is O is usually the union of some intervals, no? So it's the integral of this interval, let's say AI bi. So I is AI bi of the difference HF. I did something here with respect to the standard definition. The standard definition is that I should compute with the absolute value. No? Why I don't put the absolute? Why? Monotone is positive. Okay, equal to. Now I come cancel the next step. Let me see if I do this way or I do something different. Okay, so let's compute this. This is the sum over I, 1 over h, ai, bi, f of x plus h minus f of x. But now I can make a change of variable, no? Period is equal to, okay, you see. So let's define, okay, so let's do the thing. So for one interval, I'm integrating the integral translated here minus the value translated here. So it's something like, essentially, so let's say this is the integral here minus the integral here. Okay? So well, I can say that this is equal to the integral from 0 to h of f of the sum over I. This is f of bi plus h minus f over ai plus h. Because it's something like adding this with minus and this one with plus. It's the same computation we had before when we compute the integral of this guy when h goes to 0 converts to the f of a minus f of b. And here, well, I just observe I have this one with a plus, this one with a minus, I just add the interval in between, and then it is the integral from 0 to h of the translation for each interval. And then the sum can enter because the integral is continuous with respect to countable sum, if the function is positive or a 1. Okay, now let's look at this guy here. For fixed, so here I'm integrating, sorry, let's say, sorry, here is a mistake. Y, and these I integrate in dy. For each, so you see the picture, no? I'm integrating with this with a minus and this with a plus. They are translated by h, so I just integrate on the whole two intervals. And this part is the same, so they cancel. So now let's look at this guy here, for y fixed. What is for y fixed? So essentially, let's say this is the small set that I take, O, and it is O translated by y. So is the difference of f on the set O translated by y. Just y fixed is just the translation. But then I know it is absolutely continuous. And the measure of open set is less than delta. So for all y, the sum f of bi plus y minus f of ai plus y is less or equal, is less than epsilon. Because f is absolutely continuous. And the measure of O plus y is equal to the measure of O. The measure is translation invariant, less than delta. Okay. Okay, so this object here for any y is less than epsilon. So that this is less than epsilon 1 over h, the integral from 0 to h, which is equal to epsilon. Conclusion. I know it seems magic, but it's just a change of variable. Conclusion. Uniform continuous. Conclusion, by Vitali, I can pass to the limit, I have the equality.
We don't need tightness.
You know me?
Tightness.
Because we are in a bounded interval. Are you lost? A little bit. I can do more pictures, but I think this picture is, this is the step here, and this is just the step here, so it's direct, no? And that is the theorem, so it's very, maybe it's a nonlinear way of giving the proof, but understand how it decomposes, not theorem. Let's do a stupid exercise, because I think let's put quantum increase just to simplify. Why is that so? This is an exercise just to work with the definition. Why is that so? Take an open set containing that set, whose measure is arbitrarily small. Then the image is a measure which is arbitrarily small and clearly contains the image of the original set. So the measure of this guy is arbitrarily small. This one. Absolutely continuous in epsilon 1 for epsilon greater than 0. Is F absolutely continuous in 0, 1? Okay, so if you do with the definition, maybe it's just a little bit cumbersome. You just you take and now we know all the equivalent definitions. Equivalent definition is just look here. So something like saying that G is L1 for in every interval epsilon 1 is G in L1 is 0, 1. Yes or no?
Almost 0, yes, because measure is 0 anyway. It's not bounded, so.
But not bound, because you just require that it can blow up. If it is uniformly bound. Yes. How to make it uniformly bound?
Uniformly continuous? there exists n. There exists n for every epsilon model x smaller than. First, we need there exists m.
Why m?
M, I mean that m is same for every epsilon. We need to find
monotone increasing. Yes, by monotone convergence theorem. Because this is like the integral f you understand? Question here, please ask now, because the exercises are more or less like this one. This is just a sketch. I want to see how much you understand. So the assumption is that this guy hold. And then I have the observation that t is equal to this integral. And then t is equal to this integral. This is less or equal than this value, sorry. So you have a family of function which is positive, and when epsilon goes to 0, they monotonically increase. Bounded, so the integral exists and is bounded by the monotone convergence theorem, because the limit of this guy converges to the integral of f prime, sorry, from 0 to 1, and is uniformly bounded. Okay, so we have done all this stuff, this part. Another exercise which is a little more difficult, but is very important. G bounded. F AC. Then change of variable formulas for absolutely continuous function. How to prove? That is not an exercise for, it's just that you need to know that you can do this option. So let me sketch. Okay, if it holds for, I need some implication, because G bounded is a complicated object. So let's go back to something easier and easier, and finally we get this. For example, let's start with the monotone, with G positive.
G positive.
If it holds for G positive, does this imply the result?
I think it's true for bounded variation functions. We have some
Here?
Because P is bounded, total variation is bounded, G bounded, so still this is.
This can be this is here you have to place with a measure in continuity. I tell you, so it's not that easy. We need absolutely continuous is the fact that this object is exactly the derivative of f. Otherwise, the derivative of f has singular parts that we are not like the Vitali function. For the Vitali function, this is false, because the Vitali function has derivative 0, and the image should be the integral 0 for any function, which is clearly not true. No, you need absolutely continuous. So, how a statement like this one well, it seems complicated, but you always go back to simplify object, because at the end the theory starts with very simple objects, which are intervals. And then everything is built by a limit procedure starting with intervals. So now you have to invert the route, going back from complicated object to intervals, and then show that for intervals this is really true. Already, what do you prefer? I start with intervals, I build G, or I just go back? What do you prefer? My way of thinking is that I just take G and simplify until I arrive what is the bottom. Or I start with the bottom, but still I don't know which is the bottom. So let me do it this way, my way. If G is greater or equal than 0, so suppose hold for then holds for general G. Is that true? Yes, G can be decomposed into the positive and negative part, and clearly, sorry, here I need something because strictly monotone. Otherwise there is a sign in between. In some sense you can make it, can give some name, but let's say strictly monotone, so it's better.
L is strictly monotone?
Yeah. So the change of variable is fine, otherwise the counter image is more than 1 point. But still the formula is true. But okay, we take it. So if it holds for positive, then it holds for general G, simply because G is the sum, these are linear functionals in G. So let's say suppose it holds for a sequence which is increasing to G. Then it holds for G. But yes, the monotone convergent theorem, because this object is positive, this is positive, they increase. Okay, so now let's take the Gn.
Simple functions.
Simple functions. At the end, the route is always the same. We're just going backward instead of going forward. So simple functions. And then simplify again. And then sets, indicator function of sets. So the measure of E. So now this is the measure of f to the minus 1 of E of f prime x dx, or vice versa, the measure of f of E is equal to the integral of E of f prime. It's the same, no? Because it's f is inverted. Simplify again. Instead of having sets, it's enough to build for open intervals. And that is just a state of absolute continuity. Because this is exactly the measure of the interval f of b, f of a. And this is the integral over the interval b, a. Okay, so you see that at the end you can always build everything from the beginning. The problem is to do the line, but the line is always the same. Either you start with open and go up, or you start with whatever you have and go down. And at the end you reach something, a statement for you're starting the building blocks, which are just open sets. So I need still one class of functions with an important inequality. So are there questions here? This is in some senses the core of the course, is this theorem. Not because, well, you can extend measure theory to other stuff, but this is an important class of time, very important class. You can do change of variables, you have the derivative, and so it is the very important class of function.
What is next? About convex functions?
Convex, now we talk about convex, and then we do just do a crash course of 1 hour about the extension of the measure theory and other 3 theorems without proof. So we just do the theorems, some example how to apply the theorems. Because I don't have time to do the proof, unfortunately. It's always like that. But let me tell something, that in any case, the proof of that theorem is always built like along this line. So you make a statement for a complicated object, which is this is G, in the other case is a measure, and then you prove that if it holds for that object, then it holds for much simpler object. At the end, you're required to hold for a very simple object, and in that case is the definition. If you see, all the proofs are built in this way. You always go back to whatever you have. And another thing is that it's very easy to make mistakes here. So I really suggest if you work in real analysis, always try to reproduce all the proofs. It's very easy to make mistakes. And the literature is full of mistakes about real analysis. Because it's subtle, it's a little bit subtle. All you see is, it seems so easy, the line, but maybe there's a gap inside. It seems so clear, but actually sometimes you make something clear, then you discover, gosh, there is this bad set and you just forgot. So convex functions here. Okay, so for fun, let's find what is your feeling about convex function and which is your natural definition. Well, convex function can be a drawing. I draw the convex function. Yours okay? So let's say, is this convex?
No, we have some.
No, it's not. Okay, so you know when
Yes,
it's convex. Okay, so now I need the definition.
For every t belongs to 1 is 0, tx plus 1 means t.
You know it, okay. Like a focus set. Now take 2 points, take the segment, and then the function is below the segment. So I'm trying to say that the epigraph of this region over here is convex. Okay. Oh, now about the domain of definition. Here there is always this problem. So the domain can be R, is an open interval, to the interval, whatever. So let's take R, we don't discuss. Clearly at the end it happens the following. So you have a domain, so it is bounded in some interval. So let's say it's bounded in the open interval AB. And you take, so it's bounded, it's defining an open interval, and then in every sub-intervals is bounded. Exercise. Phi less than plus infinity in AB, then phi is bounded, so let's say in every interval CD, compact interval components in AB. I leave you by exercises.
Speak.
Okay.
It's bounded by the measurement of the same of this segment.
It's bounded above by the segment, certainly, and
By
below.
the maximum and below also.
Below why? Because if you go to maximum infinity,
Well, because of this subject.
let's do that. I leave it as an exercise. So, let's start with the definition. So we choose this definition here. This is the point here, so let's say this is x, and this is y, and then this is the point 1 minus lambda. Sorry, 1 minus lambda, lambda, L. The point in the segment, which is this point here. The value is the coordinate of this point, and here is the value of the function at that point. Okay, let's do some. So let's compare. And now let's compare with the drawing 2 points like this one. What you can say about the slope, or let's say the triangle. All the proofs are just exercises, but let's write with the step. So this is x, and this is z, and this is y. Or let's say this is y, and this is z. Okay. So which statement I can say about the slopes of these segments?
This slope is bigger.
So which is the smallest? So phi of y minus phi of x is y minus x, which is the intermediate, the middle one. This one. Because I have 4 children, they talk to me all day, and then become deaf, I'm sorry. And then?
Phi of z minus phi of y. Is this the equivalent to the, or one of the two? Is it equivalent to the, for example, this one to this one? Is the, is that equivalent to convexity? Yeah, it's equivalent. It's just by the door. So if for any 3 points, the point in between has this level, clearly this value is below that one. So equivalent definition. So let's go on now. I discover something nice. So what about the limit when y converges from the right to x? If differentiable, so
The limit is not what these are taken from one side.
It's bounded.
It's bounded, yes, but it's also.
The derivative.
Well, let's see. When y is less than z, his incremental ratio is decreasing.
yes.
So the limit from the right of the incremental ratio exists, and it converges to something. So the derivative from the right. From positive, no? Sorry, phi. Exists. Because this is a monotone, this is decreasing. So the limit exists. And also, the minus phi is the limit now for h less than 0, going to 0 of the same ratio. Because it's the other, no? You look from this one, you have that when when y converges to z, that thing is larger than from x, which is more distant to z. Okay. But I have even something more, no? So I know that this is decreasing. Is that bounded from below or can go to minus infinity? Take a point x here. So this point x here. So how to control this ratio, the slope of this interval? Just take another point here, take this slope, clearly by the very same inequality, all the incremental ratios are bounded by the slope of this guy. So and bounded in the interval of definition. But even more, it's uniformly bounded in every compact sum interval. Because this estimate holds for all points from this onward. So we know that d plus phi, d minus phi so there exists, for, let's say, the statement is like this. For all C, D contained in AB, there exists M sufficiently large such that D minus phi less or equal to D plus phi in every point Just look at the drawing, no? This slope here, where this is the point C, certainly controls all the slopes from below, all the slopes on this side. Now, if you take a slope here, this certainly controls all the slopes from that side. So M is just the maximum. Give me CD, I find which is M. And then what I know also is that are they increasing, decreasing? Increasing. And can I say something also? So for example, the derivative, the plus derivative in x and the minus derivative in z. Plus phi in x is less than the minus phi in z. I know they exist, and O is just this definition, which is equivalent to that definition. So exercise. Now I am question. Can they be different? Sorry? Can they be different? Yeah. But in how many points? The discussion is always that one. So let's see. For A, if I take 2 points like this one, so I know that the plus here, D plus, is less or equal than D minus here, which is larger than D plus, D minus here, that is lower than D plus. So the points, how many points they are bounded, and in how many points they can be different.
Finite.
Count them. Countable because every time there is a jump, so you know that from now onward D minus has the same jump. And how many jumps can have a D minus? Being monotone, only countable. So we discovered that phi is differentiable almost everywhere, and phi prime is less or equal than m in every, so there exists a compact interval.
Is there one compaction? Is there one compaction?
Yeah, for prime is. But it's really bounded, it's a little bit more. L1 gives the absolutely continuous, but assume that the derivative is bounded. What can you prove? So for example, is phi absolutely continuous? The incremental ratio are controlled by the m, the very same m. It's just a piece. So the incremental ratio means that when you sum up for intervals, you get m times the length of the sum of the length of the interval. So certainly it's usually continuous, and actually you have that the delta is chosen epsilon divided by m. So now we have that phi is the integral of its derivative, which is bounded by m, and so it is Lipschitz in every compact sum interval. So you can allow something like you have a small bump, no? That's fine for a convex function. So it's not that the derivative exists everywhere. It does exist out of countable unit points. Right, but I think this is just okay. Let's do the most important inequality here. Okay. Let's do another example, a final exercise. Take any point, take x inside the interval, and L is between, let's say, d minus phi in x, d plus phi of x. Then I will apply phi of y is larger or equal than phi of x plus L y minus x. So so here is one slope, the other slope, I'm taking a slope in between, and I'm saying that is equality code. You agree or not? Well, is a consequence of exactly what I wrote the inequality about the slopes, no? Because you pass to the limit, now you have this series of inequality, you pass to the limit to this guy, and then you obtain that this holds, and pass the limit to the height, you have the other thing, then you put them together. But just at the draw, no, you agree?
Yes, it's true if Y is bigger than x, so it's.
Y is bigger than x, you can take the plus.
Yes, this one.
And then clearly the minus is less or equal, so the inequality holds also for all values in between.
Yes.
Now let's say the Jensen's inequality. So I'm computing phi of the integral from 0 to 1 of like, we take a bounded function just to be sure that assumes value inside the interval. But the problem is just to control that the values are compatible. You can compute this object. Sorry, the integral of phi f of x dx.
Phi is continuous.
Yeah, we assume, so let's say f from 0 to 1 maps to, let's say, a. In order not to have problems with the integration, because the function is going to plus infinity, so it just can be plus infinity the value. Okay, so for the proof, let's do for 2. For very simple, assume that f is has just finitely many values. Of some set ei. So this becomes phi. This is the sum ci, and this is the measure of ei. So from that, it means that the measure of ei is equal to 1. Why?
Because interval.
From 0 to 1. It's a partition. Sorry.
Yes, this is Ian Jensen's equal for discrete.
Yes.
Yes.
And now?
Yes.
Is this one? Not just for 2?
For some n over.
For n. So it's okay by the very definition for n. Extended to n. 2 endpoints. So let's say this is goes to endpoints. And values. So if you take n points, take a linear combination with the convex combination, which is exactly some. So let me write it. If sum over alpha I equal to 1, alpha I greater equal than 0, xi are in the interval, then so the phi of the sum alpha I xi less or equal than phi the sum alpha I phi xi. This is the extension that I apply here where the alpha I are the measure. So now if you want to use the standard, you pass to the limit. Or now we do another proof, which is the proof that you find in the books and is based on this part. Take x equal to this integral. Then write phi of f of y is greater or equal to phi of the integral plus L, whatever is L, f of y minus the integral. Is exactly that form. Integrated both sides. This is this object This is the other object, and this is 0 because it's the integral y minus the integral of y. This is shorter, I make a use, but you see that at the end, if I want to go with my standard route, the bottom I can do that. Still I can always do that. Okay, I'm sorry, I used a little bit more time, I wanted to finish this. And that's it. This is the key point, remember the key point is that the sum, the total measure is 1. That's the key point. Because complex combination requires that the sum of the positive weights is 1. So I think it's Wednesday, the next one, no?
If you can.
So I'd like to prepare send you the exam scores. So we just try. Bye-bye.
I think we're gonna take this classroom, the next, right next to here, because there's a class, yeah, and there's a class here.
Is that clear? There is a toilet?
Yeah, he said
Because
today.
I just did this.
Yeah, he said today at the same time. So
Are you staying?
I think so.
Are you?
Just because I asked. Yeah. Yeah, now I feel like.
Are you staying?
3 hours
Okay.
ago.
What did you say that?
Yeah, I know.